Okay, so load following we have seen it. So previously in that we saw a couple of problems, but not solved, but one of them I will solve it. So this is actually that in your deregulated environment, that problem also I told you earlier to solve, but I will solve it for you now. Before, maybe after this one more, and after that we will go for another topic. So consider a two area interconnected power system. Area 1 consists of 2 GENCOs and 2 DISCOs, that is 2 generation companies and 2 distribution companies, and area 2 also consists of 2 GENCOs and 2 DISCOs, right. Contract participation factor are CPF 11 is equal to 0.4, CPF 21 is equal to 0.3, CPF 31 is equal to 0.10, CPF 41 is 0.20, CPF 12 is equal to CPF 22 is equal to CPF 32 is equal to CPF 42 is equal to 0.25, all are same. CPF 13 is equal to CPF 23 is equal to 0.0, CPF 33 is equal to CPF 43 is equal to 0.50, and CPF 14 is equal to 0.30, CPF 24 is 0, CPF 34 0.70 and CPF 44 0 is equal to 0. Assume that each DISCO demands 0.10 per unit megawatt power from GENCOs and defined by contract participation factors, and each GENCO participates in AGC as defined by following AC participation factor. That AC participation factors are given as A-11 is equal to 0.75, A-12 is equal to 0.25 and A-21 is equal to A-22 is equal to 0.5, right. So determine the output of each GENCO in the steady state. Also determine the scheduled power flow on the tie line and its direction. If DISCO 1 in area 1 and DISCO 4 in area 2 demands 0.10 per unit megawatt each of excess power, calculate the output of each GENCO in the steady state. Note that GENCO 1, GENCO 2, DISCO 1, DISCO 2 are in area 1 and GENCO 3, GENCO 4, DISCO 3 and DISCO 4 are in area 2. Here somehow scanning cut, GENCO 3, GENCO 4, DISCO 3 and DISCO 4 are in this one. So if you look into that if DISCO 1 in area 1 and DISCO 4 in area 2 demands 0.10 per unit megawatt each of excess power, we have to calculate this one, right. So solution I have to write it here. So in this case your sorry, just hold on, right. So whatever distribution participation matrix is given, so we can write here the DPM, whatever is given here. Look, no notes are here. So when you will listen to this, you please note down all these things, right. Just 1 minute. So first I have to make it that there are 4 distribution companies. To accommodate the space, instead of your DISCO 1, DISCO 2, DISCO 3 and DISCO 4, I will write D1, D2, D3, D4. Similarly, GENCO 1, GENCO 2, GENCO 3 and GENCO 4, in short I will write G1, G2, G3 and G4. So in that way my DPM is equal to, say this is I will write D1, D2, D3, D4, that is DISCO 1, DISCO 2, DISCO 3 and DISCO 4, and this is my GENCO 1, G1, G2, G3 and G4, right. So next I will put those whatever your contract participation factors are given. So I will write here it was 0.40, right, then 0.25, then it was 0.0 and it was 0.30, right. Similarly, this one CPF 21 0.30, 0.25, then it was 0.0 and 0.0. Similarly, for GENCO CPF 31 all were given, I am just writing 0.10, 0.25, 0.50 and 0.70, right, and 4142 like this 0.20, 0.25, then 0.50 and 0.0. This is my DPM. this is disco 1, disco 2, this way we write, right. If you add all this column, you will find this all this summation of this is unity, right. If you add this one, it is unity, this is unity, this is also unity, this is also unity, right. And you have your what you call that you have that then 4 distribution companies. So, their power demand is delta PL1, delta PL2, delta PL3 and delta PL4, right. Therefore, to find out the your what you call the steady state values of that power that has to be generated by GENCO 1, GENCO 2, GENCO 3 and GENCO 4 as steady state without considering the uncontacted power demand. So, delta PGC1, right, that is nothing but whatever will come, that is contacted power demand, that is nothing but your delta PG1 steady state, right. This much power will be generated. So, that should be is equal to your, if you just multiply this one 0.4 delta PL1, then plus 0.25 delta PL2 plus 0.0 into delta PL3 plus 0.0 into delta PL4, the first row, this first row, and delta PL1, delta PL2, delta PL3 and delta PL4. So, delta PL1 all are given 0.1, delta PL1 is equal to delta PL2 is equal to delta PL3 is equal to delta PL4 is equal to 0.10 per unit megawatt, all are same, right. Therefore, this one will be actually 0.4 plus 0.25, right, is your delta. One thing is there, this is actually 0.30. So, this is 0.30, right. So, plus 0.30 into 0.1. So, that is actually will come your 0.095, right, 0.095 per unit megawatt, right. Therefore, the contacted power this thing your what you call delta PGC1 is equal to delta PG1 steady state is 0.095. So, I am clearing it, right. So, therefore, delta PG1 steady state is equal to delta PGC1 is equal to 0.095 per unit megawatt, right. Similarly, for delta PGC2 if you calculate, delta PGC2 if you calculate, I am writing for you, it is 0.3 plus 0.25 into 0.10, that is actually is equal to 0.055 per unit megawatt. That is equal, that is nothing but delta PG2 steady state, right. Similarly, delta PG3 steady state is equal to delta PGC3 is equal to, similar way you can calculate 0.1 plus 0.25 plus 0.5 plus 0.7 into 0.10, that actually comes out to be your 0.155 per unit megawatt, right. Similarly, delta PGC4 that should be is equal to your whatever I have calculated 0.25 plus 0.25 plus 0.50 into 0.10, right, that is equal to actually 0.10 per unit megawatt, right. So, this is actually your what you call that all these calculations I made for you, this is actually for your steady state error, that not steady state error, that whatever power will be generated by this your GENCOs, right, at the steady state. So, this is one, then this is another one delta PG2 steady state, this is delta PG3 steady state and this is delta PG4 steady state, right. So, now I am cleaning this. So, now it is given AC participation factor is given that A dash 11 is equal to 0.75, right. then A dash 1 2 is given, that is your then 0.25. Similarly, A dash 2 1 it is 0.50, it is given, and A dash 2 2 is equal to also 0.50. So, AC participation factor is given, right. Therefore, that delta Pg1 steady state, right, is equal to that contracted power demand delta Pgc1, right, plus your A dash 1 1 into that your what you call the your that uncontracted power demand was 0.1. So, that will be 0.10 because uncontracted power demand was 0.10, right, in area 1. So, that is actually delta Pg C1 was 0.095, that we have calculated into plus 0.75 into 0.10. So, that actually comes out to be your, if you add this thing, it will be 0.17 per unit megawatt. This is delta Pg1 steady state, right. So, similarly, your delta Pg2 steady state. So, I am clearing this, right. Similarly, delta Pg2 steady state is equal to your delta Pgc2 plus your A dash 1 2 into again that uncontracted power demand was 0.10. So, delta Pgc2 it was actually 0.055 and this was 0.25 into 0.10. So, that is actually coming to be 0.08 per unit megawatt, right. So, this is delta Pg2. Similarly, that your A dash 2 1 is equal to A dash 2 2 is equal to 0.50, right. Therefore, delta Pg3 steady state, that is your when uncontracted power demand was there. When it was not there, then there is that we have done it. When uncontracted power demand was there in area 2 also. So, in that case your this one will be delta Pgc3 plus A dash 2 1 into that 0.10 because, right. So, this delta Pgc3 we have calculated, it was 0.155 plus 0.50 into 0.10, right. So, it comes around 0.205 per unit megawatt. This is when uncontracted power demand is there. That is why this term, previous case also, here case this term is coming. Similarly, delta Pg4 steady state when uncontracted power demand was there, right, is equal to delta Pgc4 plus A dash 2 2, again uncontracted power demand was 0.10. So, directly multiply. So, that delta Pgc4 it was actually 0.10 plus 0.5 into 0.10. So, it comes out to be your this is actually 0.25 because 0.25. So, sorry, it was 0.5, sorry 0.5, just making it 0.5 into this one. So, it is coming around 0. Your what you call 15 per unit megawatt, right. So, this is the steady state when uncontracted power demand is there, because uncontracted power demand will be distributed as per the way you have defined the AC participation factor, right. So, this is done. So, another thing is that your tie line power flow, right. As each areas there are 2 GENCOs and 2 DISCOs. So, this is my area 1, this is already we have done it, but this is say DISCO 1, this is DISCO 2, this is GENCO 1, GENCO 2 and this is that tie line, right, and this is my DISCO 3 and DISCO 4 and this is GENCO 3, GENCO 4, right, and direction is this way. I think it has been asked, find out the direction of the tie line power flow. So, in this is area 1 and this is area 2, and therefore, the way we have taken the direction, it is delta p tie 1 2. So, from that if I recall correctly that equation delta p tie 1 2, I think equation I have forgotten the equation number, perhaps it is equation 4 or 5, right. So, delta p tie 1 2. So, if you expand that equation, delta p tie 1 2 is equal to, I am writing here Cpf 1 3, I told you how to make it, right. Delta PL 3 plus Cpf 1 4 delta PL 4, right, plus Cpf 2 3 delta PL 3 plus Cpf 2 4 delta PL 4, right. This one minus in bracket that Cpf 3 1 delta PL 1 plus your Cpf 3 2 delta PL 2 plus Cpf 4 1 delta PL 1 plus Cpf 4 2 delta PL 2, right. So, this thing we know, right. Now, if you substitute all this value and try to calculate, right. So, I am just clearing this one. So, if you calculate, then delta p tie 1 2 should be is equal to your 0.0 plus 0.30 plus 0.0 plus 0.0 into 0.10 minus, right, 0.1 plus 0.25 plus 0.20 plus 0.25 into 0.10. Therefore, this actually comes out to be minus 0.05 per unit megawatt. That is 1 to 2, it is minus, that means power actually flowing in the direction of delta p tie 2 1 is equal to then 0.05 per unit megawatt. That means power is flowing from 2 to area 2 to area 1, right. So, just when I am making all these small calculations and this, so I will request you that if you find any error in my calculation or other thing, you just either put the question in the forum, we will rectify that, and or you can send me a mail also, right. So, this is that problem. I thought another is there that you will solve it, right. So, after this another small thing we will take, that suppose this is another example, right. Suppose you have one area, two area only, suppose you have 3 distribution companies area 1 D1, D2, D3, right, and you have 2 generation companies G1, G2, and this is your tie line, right, and in area 2 this is your area 2, right. Here we have 2 distribution companies D4, D5 and only one generating company, that is Genco 3, right. So, Disco 1, Disco 2, Disco 3, in short we make D1, D2, D3, and this is area 1 and this is my area 2, right. And say for example, power is flowing in this direction. So, this is delta p tie 1 2, right. So, we have to find out that delta p tie 1 2, right. So, first we have to see that the DPM, Disco participation matrix. So, in this case Disco participation matrix you will write like this, you have 3 generation companies. So, making it here, right, say this is you make G1, G2 and G3, this way you will make, and then you have 5 distribution companies, you write D1, D2, D3, D4 and D5, this way you write, right. Then you make CPF 1 1, then CPF 1 2, then CPF 1 3, then CPF 1 4, then CPF 1 5, right. Then this one also you make CPF 2 1, CPF 2 2, CPF 2 3, CPF 2 4 and CPF 2 5, right. And then last one CPF 3 1, So, CPF 32, CPF 33, CPF 34 and then CPF 35, right, and 5 discos are there. So, each disco demanding delta PL1, delta PL2, delta PL3, delta PL4 and delta PL5 power demands, right. So, this is say I am writing delta your what you call, this is I am writing say delta PL1, delta PL2, delta PL3, delta PL4 and delta PL5. Just right hand side I wrote delta PL1, delta PL2, delta PL3, delta PL4, delta PL5, right. Now, what will be the expression? Now, I am just hold on, I will change the color, right. So, now I want to find out what is my delta expression for delta p ti 1 2. What is my delta p ti 1 2, right. So, look that distribution companies D4 and D5, right. This D4 and D5 that it can have contract with G1 and G2. That means, if D4 D5 distribution companies here, if it draws power from area 1 GENCOs in area 1, so power will flow from 1 to 2, right. So, that thing we take positive, and another thing is that D1, D2, D3 has contact with G3. So, power basically this power, their power from here it will flow to this, that is why we take minus, such the resultant one in the direction of 1 2. So, that means, if you look into this, that D4 and D5 in area 2. So, this is my D4 and D5, right. So, this is in area 2 and it will draw power, right, from G1 and your what you call G2, right. That is here these two GENCOs are in area 1, right. So, in that case what will happen, that this one, that D4 and D5 drawing power from G1 and G2, and if you look into that D4 has contact with G1, that is CPF 14, and D5 has contact with G1 CPF 15. Similarly, D4 has contact with G2 because these two are in area 1, that is CPF 24, and D5 also has contact with G2, say CPF 25. That means, this block first we will consider, right, in the direction of 1 to 2. That means, that CPF 14, that delta p ti 1 2 will be CPF 14, then your delta PL4 plus CPF 15, then delta PL5, right. So, this one, then your what you call, that is 14 15. Now, plus that CPF 24 delta PL4 plus CPF 25 delta PL5. This is the power that this D4 and D5 has contact with G1 and G2. So, it is moving this way, right. Now, minus that D1, D2, D3 has contact say with G3. So, power will going to from this to that. So, resultant will take, that is why this is minus, right. Then if you look into that D4 your what you call D1, D2, D3, that means this one and this one, that is in area 1 has contact with G3, that is D1 has contact participation factor say CPF 31, this is D2 has contact CPF 32 and this one has contact CPF 33, right. So, if it is so, that means this block you consider only this part, right. Therefore, minus it will be CPF 31 delta PL1 plus CPF 32 delta PL2, right, plus CPF 33 delta PL3. This will be the expression for tie line power flow. Hope handwriting is little bit this thing, because it is a digital screen, right, digital pen, right. So, question is that now we have understood that the D4 D5 has contact with G1 G2 in the direction of 1 to 2 power will flow. That is why CPF 14 delta PL4 plus CPF 15 delta PL5, right. So, plus CPF 24 delta PL4 plus CPF 25 delta PL5, right, minus this D1 D2 D3 has contact with G3. So, CPF 31 delta PL1 plus CPF 32 delta PL2 plus CPF 33 delta PL3. So, this is the expression of tie line power flow. That means, it is not necessarily mean that how many discos and how many gencos will be there in area. So, this matrix in this case, this matrix actually that DPM is actually 3 into 5, right. So, 3 rows 5 columns, right. So, that is your what you call that that concept of disco participation matrix, and to find out what is delta p I want to, right. So, this way you can calculate that what will be that steady state contact participation that your contact power demand with each GENCOs, right. So, generally it will be CPF 11 delta PL 1 for GENCO 1, CPF 12 delta PL 2 plus CPF 13 delta PL 3 plus CPF 14 delta PL 4 plus CPF 15 delta PL 5, right. This way 3 GENCOs directly it can be obtained, right. With this that load following we have and that our AGC in restructured power system more or less many things are there on that, but I have to skip that considering that it is a video course and I have to see from the point of view of the classroom exercise, right. So, hope things are not at all difficult. As far as exam purpose is concerned, we will only consider the steady state part, right, but simulation result I showed you for the better understanding and what exactly is happening, right. And so, next we will move to, just hold on, next we will move to that your little bit on reactive power and voltage control, right. So, reactive power and voltage control, but we will not try to couple it, if time permits I will see, right. So, reactive power and generally at the beginning of the that load frequency control or automatic generation control part, I told you that if for a small change in the real power load, right, that it affects actually the system frequency, hence the speed, right, of the speed of the synchronous generator, but it does not actually affect the bus voltage magnitude. Similarly, a small change in reactive power actually is essentially it actually does not affect the system frequency, but it affects the bus voltage magnitude, just vice versa. That is why we call PF, that is real power frequency control or reactive power voltage control, right. So, little bit we will see it here. So, actually the generator excitation system maintains generator voltage and controls the reactive power flow, right. So, the generator excitations of older systems may be provided through slip rings and brushes by means of DC generators mounted on the same shaft as the rotor of the synchronous machine. However, modern excitation systems usually use AC generators with rotating rectifiers and are known as brushless excitation. Several types of excitation systems are there. So, in this course perhaps I will not find time. If I find little bit, because after finishing this we will move to state estimation. If after state estimation if time permits, then I will derive that your block I derive that your what you call that hydro turbine modeling, right, that is for AGC, suitable for AGC. And after that I think we will not find time to excitation system, because different type of excitation systems are there and it will take time to explain, right. So, as we have seen, a change in the real power demand affects essentially the frequency I told you, whereas a change in the reactive power affects mainly the bus voltage magnitude, right. So, interaction between voltage and frequency controls is generally weak enough to justify their analysis separately, right. So, the sources of reactive power are generators, that is synchronous generators, capacitors and reactors, right. The generator reactive powers are controlled by field excitation. So, thank you very much, we will be back again.